Hey everybody, let's give this second order circuit a try. So the switch has been closed, so it's closed for a long time. Okay, so if it's a long time, the voltage and current everywhere is constant. So for this capacitor, the current would be C dV dt, and this voltage would be constant, which means dV dt, the time derivative, would be 0. So the current here is 0 for the capacitor, which means all the current goes, right, so from this voltage source, there's current coming, and then all of it goes this way, none of it goes this way. Okay, so all of that current goes this way, so that means also the voltage across this inductor, would be L di dt. This current would be constant, so di dt, the time derivative, would be 0. So to say the voltage across this inductor is 0 is like it's a wire, right? It's just a short. Okay, so then what does it look like? It looks like an 80 volt source going to this 300 ohm resistor, and then this 500 ohm resistor, and then a wire. That inductor behaves like a wire. And then no current goes through this capacitor. Right? So it basically looks like this. So the voltage across this inductor was 0, which means it's a wire. So the voltage across this resistor, the 500 ohm resistor, would be, it's a voltage divider, right? So 80, and then so it would be 500 over 300 plus 500. Oh, so that's convenient, 80 over 800, so that's just 50 volts. Okay, so the voltage across the 500 ohm is 50, and then across the inductor is 0. Let me erase all my mess over here. Okay, so across here is 50, across here is 0, which means across here has got to be 50. Okay, so the voltage across the capacitor at t equal to 0 is 50. The current through this inductor, we don't know. At this second, we know the current going through this resistor. Right, the current going through the resistor would be V over R, 50 over 500, so 0.1 amp, 100 milliamps. And the current going through the resistor over here is the same as the current going through the inductor. So, which is also the same as the current going through the inductor at t equal to 0. Okay, so there we go. I'll just write this as current for the inductor. Okay, so we got some initial conditions here. And then when we open the switch, all of this goes away. So we're just left with these three things in series. Okay, so let's say if we go KVL counterclockwise, so, and then I'll just use that current. So we got the voltage for the resistor, IR, the voltage for the inductor, L di dt, and then the voltage for this capacitor. I know the current for the capacitor. If I want the voltage, I can move dt on this side. Right, and then I'll divide by C and then integrate both sides. So then V is V naught plus 1 over C integral I dt. Okay, which I don't want that integral in there. So we can take a time derivative of the entire equation. So then our di dt L, second derivative, the time derivative of a constant is 0, and the derivative of an integral would just leave us with I. And there we go. Okay, and then this is the highest order term, so let's move that in the front. And let's just divide everything by L. So the leading coefficient is 1. Okay, so plus. Okay, now we have this second order ODE. Let me factor a 2 out of here. Like that. Because I want to use the quadratic formula in a second. Right, so let's just do substitution. Let's call this Nieper frequency R over 2L. And let's call this omega naught squared. The undamped natural frequency. And we're going to need numbers here, so I'll plug those in the calculator in a minute. And then if we assume the solution is of some form a e to the st, we plug that in here, here, here. And then what we get is the characteristic equation, which looks like 2 alpha. Okay, which if we just plug that into the quadratic formula, we get 2 roots. Okay, which then what happens depends on if this is real or imaginary. Okay, so let me plug in numbers. So for the resistance, I'm using 500. For L, this value. For C, 40 times 10 to the minus 9. So I'll just plug that in the calculator. Okay, so they both happen to be the same number. And then when that happens, that's critically damped, right? So you can just look up the solutions from the previous lectures. What's the form of the solution when it's critically damped? It looks like some arbitrary coefficient, e to the minus alpha t. In this case, alpha is 10 to the 5, right? And then plus another arbitrary coefficient, t e to the minus alpha t. All right, so we got to solve for these two arbitrary coefficients. So we need two initial conditions, which can be the current at t equal to 0. Okay, so do we know the current at t equal to 0? Yes, we solved that earlier. Okay, so at t equal to 0, a1 e to the 0 plus a2 times 0. So that whole thing is 0 equals, and then we just said we solved it earlier, it's 0.1. Okay, so a1 is 0.1, so we're halfway there. How do we get a2? We need another initial condition. We can take the time derivative of this equation. Okay, I'll just do, okay, so time derivative. Maybe I can pause the video and I'll just write it. Okay, right, so I just took the time derivative of this, then I got this. Note that this is a product, so that I use the product rule here. Okay, di dt, what is that? Multiple choice. We have for a capacitor, and then for an inductor, right? So di dt shows up here for an inductor, right? So for example, if I just rearrange, right, just move L on this side. This is the same as V for the inductor over L, the inductance. Do we know that information? Because what I want to do is have this at t equal to 0. At t equal to 0, because, right, for this, set t equal to 0. Minus alpha a1 e to the 0, which is 1, plus a2 e to the 0, which is 1. And then there's a 0 right there, so this whole thing is 0. Equals the voltage across the inductor at t equal to 0. Do we know that information? We knew the voltage let's just say this way. For the inductor, oh, it looks like I erased it. Okay. Remember that it looks like this? Before the current was going, it was a constant. This is a constant, so di dt is 0. So then the voltage across the inductor was 0, right? It was behaving like a wire, a short. So for this particular circuit, the voltage across that inductor was just 0. Not always, just for this particular example. Okay, so then let me just rewrite this. Minus alpha. Alpha is 10 to the 5, right? There we go. Right, and then A1 is 0.1, right? 0.1. So A2 is just 0.1 times 10 to the 5. Okay, so A1 is 0.1 and A2 has got to be 10 to the 4. So there we go. And you just plug those two numbers in right here. And there's your answer. Why don't I just copy and paste that? Okay, so A1 was 0.1 and A2 is 0.1 times 10 to the 5. So that'd be 10 to the 4. And there we go. 10,000, right? I'll just write 10,000. There we go. Okay, that's part A. Part B is, I'll just copy this. All right, so let's solve for the voltage across the capacitor. All right, so we're going around, let's say this way, KVL. Let me just write generically, right? So we got the voltage for the resistor plus the voltage for the inductor plus, well, the way this is labeled, that's going the other way, right? So I'll just call that minus VO, which is what we're trying to solve for, equals 0. All right, we're trying to solve for this. All right, so VO is what we're looking for, is VR plus VL. So the voltage across the resistor, we know it's IR. And I mean, this is this, right? Which we solved that already in part A. And then the voltage across the inductor is L di dt. So then we just need the time derivative of this, which actually is right here. Okay, so this, why don't I just copy and paste things? So V of t is R times this. All right, so that was easy copy and pasting. Plus L times di dt, which is this. Okay, done. Sort of. There's a little bit of work because look, these are arbitrary coefficients. So let me just take a minute to gather terms here. So you see there's a t e to the at. Let me gather those terms. And then there's the other ones e to the minus alpha t. Let me gather those first. Okay, so this one is 0.1 r. And then this one minus L alpha A1. And then this one plus L A2. All of this times e to the minus alpha t. Okay, and then let me gather this one. So that's 10,000 r. And then this one is minus L alpha A2 t e to the minus alpha t. So if you look at it, right, see there's arbitrary coefficients. So they're arbitrary, which means why don't I just call this some other letter? I'll call it B1. I'll call this B2. Right? Because this whole thing is arbitrary. This whole thing is arbitrary. So let me rewrite it so it looks simpler. Arbitrary coefficient e to the minus alpha t plus another arbitrary coefficient t e to the minus alpha t. So now we just need to solve for these two things, and then we're done. Okay, so how do we do that? Let's use initial conditions. V at t equal to 0. All right, so b1 e to the 0 plus b2 times 0. So this whole thing is 0. And e to the 0 is 1. I'll just leave it like that, right? Equals, do we know the voltage? The voltage where again? Across the capacitor. Do we know the voltage across the capacitor when t equal to 0? Yes, that was like the very first thing we did. It was 50 volts. Okay, so that is 50 volts. All right, so B1 is 50, halfway done. What's B2? The other initial condition we can solve for the time derivative, dv dt. Okay, and then let me just jot that down real quick. Okay, so I'm going to take the time derivative of this. I'll just do it quick. Plus b2t. Derivative of t is 1. And then minus alpha b2t e to. Okay, I just took the time derivative of this, which is this. And then now we set t equal to 0. Right, so minus alpha b1 e to the 0, which is 1. b2 e to the 0. And then there's a t over here, so this whole thing is 0. And then dv dt, remember, for a capacitor, C dv dt. For an inductor, L di dt. We wanted dv dt, which just shows up here. So we're trying to look at the capacitor. So just move this on this side of the equation for the capacitor. So do we know the current going through the capacitor at t equal to 0? We know the current going through the inductor was 0.1. Let's be careful looking at the arrows though. Okay, so for the capacitor, if I label the current for the capacitor going like this, and if I label the current for the inductor going like this, I already know this answer was 0.1. So, right, it's going this way is 0.1. So going up, we should draw a different color. Going this way is 0.1, and then it goes around counterclockwise, 0.1. So actually IC is negative IL. So it's negative 0.1. Just the way it's labeled, right? Because I didn't draw these, right? It was already on the picture. So, okay, so let's just be careful because it was labeled for us before we even started. So in this particular example, this is negative 0.1. And then what was the capacitor? Whatever that, 40 nanofarads. And there we go. Okay, so, and B1 is already 50, right? So this is 50. Alpha is 10 to the 5. So for B2, done. Plug those values in here and here, and that's the answer. Okay, so that was kind of a long problem. So pause where you need to. Let me know if you have questions, and I'll see you in the next video.